sorry to say, but it's really silly to think that a computer can be conscious. Consciousness it just is impossible with mechanical things.
My guest today is Federico Faggin. He's an Italian physicist, engineer, inventor, and entrepreneur who's had a critical role in the development of computing during the 20th century, and now is a leader in thinking about artificial intelligence as well. Federico, it's wonderful to have you with us.
Thank you. It's a pleasure.
Give us a little bit of background here. How did you come to the world of semiconductors, where you're known principally for designing the original Intel 4004 processor? How did you wind up there?
Well, I was working in Italy after graduation from university at SGS Fairchild, a company that was linked to Fairchild Semiconductor, the company that invented the integrated circuit in Silicon Valley. And in early 1968, in an exchange of engineers, I was sent to Palo Alto in the R&D of Fairchild. And there I developed the MOS silicon gate technology, which was the fundamental technology that made possible to build an entire computer with the same technology in a piece of silicon. Before that, it could not be done. You could not do dynamic random access memories. You cannot do non-volatile memories, analog devices of high capacity, and the microprocessor. So that technology made possible all the future developments in microelectronics related to making computers, which is what I did later. But the first integrated circuits, they used this technology. This technology was 5 times faster. You could put twice as many transistors. The leakage current was 500 times less than the original MOS. So this performance was so powerful that it made possible all what I said. And the first integrated circuits to use that was a device from Fairchild, the 3708, which I designed as well, and it was in production by the end of '68. Intel actually took that technology, they copied it. Saying copied is a gentle way to say it. and they decided to design dynamic RAMs with that technology, which was, of course, the fortune of Intel. But also they had a project that was waiting, a custom project where they wanted to build a computer and a CPU at that time. And the only technology that could do it was the silicon gate technology. But there was a couple of inventions that they needed, which I brought with me when I joined Intel in 1970. So I designed the first microprocessor, the 4004 at Intel, and then the first 8-bit microprocessor, the 8008, and the first high-performance microprocessor, the 8080, the Intel 8080, which was 6 times faster than the first microprocessor using P-channel technology. So with that performance, now the market really took off. Now you could really begin to the first personal computers used the 8080. There was a sufficient performance to do that, and then I started my first company. After that, Intel did not understand that microprocessor were the future. I really, for example, the 8080, they waited 9 months to let me do it, and microprocessor that I invented it, would have been so much better than what we were doing before.
Intel thought of itself as a memory company at the time, right?
Absolutely. And so I got so frustrated because we lost 9 months of the competition, because 6 months after the 8080 was in the market, Motorola, brought to market their own first microprocessor, which was the first competitor that we had. That was in 1974. So that was, I said we cannot afford to lose the battle here, because the other people are seeing this as the future. So and when to the successor to the 8080, Intel was still kind of waiting it out. I said, forget it. I'm gone. So I started my own company, Zilog, developed the Z80 microprocessor. It was the first third generation microprocessor that was twice as fast and much, much better than the 8080, though it was compatible with the 8080. And that made the fortune of Zilog. And then I started other companies. In 1986, I started a company to develop chips for neural networks to make computers that could learn. That was 40 years ago, when the people that the AI experts were laughing at us. What the hell? Neural networks will never work. What a silly idea is that? So anyway, but obviously, as you know, in the last 10 years, neural networks are the ones that solve the problems that those people were never able to solve.
Right.
So anyway, it was during that time that I became interested in neuroscience, biology, trying to understand how the brain works. And so during that time, I became interested also on consciousness, despite, of course, continuing to work as an entrepreneur, as a CEO of startup companies. And then eventually, by 2011, I decided to start 29. I started to get out of everything that I was doing to focus on the study of consciousness, trying to join physics with spirituality, with the spiritual aspect of that consciousness, shows. And so in 2011, I started a foundation, the Federico Faggin Foundation, to study consciousness and provide funds for institutes and universities that do that. And now we have finally the first scientific theory of consciousness. Scientific theories because it can make predictions and it can be falsified. So it's not just philosophy, though some physicists would like to say that, but no, it's actually a theory that can make predictions and can be falsified.
So I'd like to return to the beginning of this trajectory, to 1968, when you were at Fairchild and you came to Palo Alto. What was the atmosphere like in the semiconductor industry at the time? Did you and your colleagues understand what you were advancing and the degree to which you were at the forefront of a revolution?
It was the very beginning of the adventure. In those days, the MOS technology could hardly do several hundred gates for random logic. So not enough to make CPUs. It was slow. Bipolar was fast, but the density was very, very, very small. You could do at the most, medium scale integration, half header, not hardly a CPU on a chip. So the only technology that eventually made possible all of we see is the technology that got developed in 1968. So that was the missing link, and then everything started growing. At that time, it was pioneer land almost. The semiconductor industry had started. It started in 57, if I believe, with Fairchild. Mm-hmm. It started a little earlier with a company that predated Fairchild, but that company really never did much. So Fairchild was the real thing, and the first integrated circuit. The first silicon transistors were were sold in 59, and the first integrated circuit was sold in 61, 62. And a Swiss engineer, Jean Erny, developed the planar process, which was the way to do many transistors on a slice of silicon, on a wafer made of single crystal silicon. That was the basic invention. Is surprising that Jean Erny is never mentioned, but he is really the inventor of the integrated circuit. So Jean Erny technology then was used for bipolar integrated circuits. And in 64, 65, the first company, General Microelectronics, came out with the first commercial MOS integrated circuits. So those were the very pioneering years. I would probably venture to say that maybe 20, 30,000 people were employed in the semiconductor, in the industry, high-tech industry there in the entire Silicon Valley. Now we speak, now there are millions of them. So probably a couple million, I would think, because the entire Bay Area, both north and south of San Francisco, and also east of San Francisco, really all involved in high tech nowadays. So 7 million are involved, where in those days it was probably not even 2 million people that were inhabiting that whole area. So anyway, so it was orchards all over the place, which now there is no memory of it, but it was fun because nobody could claim that they were from Silicon Valley because there were only a few farmers there that were born there, and then everybody came from the U.S. or from other parts of the world. So Silicon Valley was a land of immigrants,
transient opportunity.
Right. Yeah.
And Tom Wolfe wrote a really wonderful essay. Perhaps you've read it about those years. Fairchild and Shockley and Intel, and traces the roots of modern Silicon Valley kind of commercial culture to that era. That at a time when business was really men in dark suits going to office towers and having formal meetings, that this was an environment where everyone kind of sat in an open bullpen and spoke to each other very informally. Was that your experience as well?
That's fairly true, though Hewlett-Packard was already there. Hewlett-Packard was had started, I believe in 1939, so just prior to the World War II. And they were making instruments, but they were people that had studied at Stanford University that started the company, Mr. Hewlett and Mr. Packard. And so there was something. There was also some other stuff going on, but really the semiconductor was the real deal there.
I imagine the process of developing a processor in those days was very tangible. I mean, you were masking out these designs physically, right? And then they'd be optically reduced. Were you actually close to the production process as well, or was it kind of abstracted the way that it is today?
The MOS silicon game was a production process. It was it was a new way of making integrated circuits. It was in those days. Of course, in those days, people that were doing the process were generally separate from the people that were doing the design of chips. But because of my sort of horizontal preparation, I actually had designed and built the small computers when I was 19 at Olivetti. So I had the entire understanding of from computers to semiconductors, the physics of semiconductors and everything else. So that's the reason why I was able to do what I did in those years, because most people were already specialized. They did not, if they understood how to make integrated circuits, they didn't know much about computers or much about architecture or logic design, maybe maximum some circuit design. And to do a microprocessor, the problem was, of course, to have the technology that could allow you to do it. It was, people knew how to make computers in those days. I knew how to design a computer, but you couldn't do it with the technology that existed. It was hard work because you had to draw a scale of 500, all the transistors, and draw it by hand. Mm-hmm. So there was no computer-aided design that would help. Then you would do a drawing that was, of course, 500 times the area. That's very difficult. In fact, if I remember correctly, there were three or four big sheets that had to be done, and they had to coincide perfectly. Mm-hmm. Because the tables were not large enough to do it. So, and also the cutting tables, where basically the different layers were obtained by cutting and stripping a thin film of red mylar, over a thicker mylar, so that you could create areas of dark and light, transparent. And that was also very painful and prone to error. So the process was extremely laborious, everything, as I said, had to be done that way. I actually did the entire computation of because Intel didn't even want me to use computers because it was too expensive to do simulations. So I developed a simple method to size the transistors in ways that would, we would avoid having to do simulations, because they, contrary to other companies that were further ahead, Intel was just started and they didn't have they didn't have logic simulators, and so for the circuit simulation, they didn't want to spend the money, and so I was able to do it with a slide rule and graphic simulations. So anyway, but it worked. So
yeah. Is the design of the 4004 something that you can completely, hold in your mind and comprehend fully, unlike, say, a modern processor where no individual can understand every detail, or even like the Google search algorithm where there's no one person who can explain every detail of what's going on. But this is something that you held entirely in your head.
Absolutely, you would know. I would know the function of every, not only transistor, but also every capacitor, every resistor. Right. And again, it was my skill with both circuit design, but also the how semiconductor works that allowed to solve the delicate problems that other people thought it were impossible to do. Those are the two inventions that I brought with me were of that ilk, meaning, one was, doing bootstrap loads with silicon gate, because everybody thought it was impossible to do. So it was also difficult for me to figure it out, but I was able to figure out how to do it. And then how to do direct contact between polysilicon and silicon so that we could have a 2-layer of interconnection. That was why it was possible to put twice as many transistors in the same area, and therefore put the 2,500 transistors or so that were necessary to build the CPU, the simplest CPU possible. So,
as you moved on to Zilog after Intel and became the CEO of your own company, did that give you a new perspective on product development? How did you temper your kind of pure engineering and physics perspective into one that was the perspective as CEO?
Well, it was the school of hard knocks, right? I mean, when I had no, though I knew how to obviously run a several projects simultaneously. For example, at Intel, I was head of one of the two departments of R&D. So I had about 80 people working for me. Most of them were engineers. And so, I had a large group that I was managing by the time I was leaving Intel. But what about finance? What about administration? What about production? What about marketing and sales? Those were all new things for me. So how do you make a business plan? Whoa, how do so, but I'm a quick study, so I was able to do it. In those days, it was almost impossible to get money on top of it. That's why we ended up having money from Exxon Enterprises, which was good in one way because we got money. In 1975, the total amount of venture capital invested in the U.S. that year was $10 million. Now,
this is what Stanford undergraduates roll out of bed and find on the floor.
Now is seed money for one company.
Right.
Seed round for one company is $10 million. So in those days, that's it. The entire I built the Z80, the development system, all the software and everything else with $400,000.
Wow.
And 11 people were the company, the minimum number of people needed to do this. Mm-hmm. And of course, I drew about 2/3 of the layout of the Z80. That's the reason why now I wear glasses. And it was I worked 80 hours a week for 5 months. I mean, it was grueling, but we had to make up also for the time lost at Intel. Mm-hmm. Because as I mentioned, I decided to leave because they were not eager to do the next one. So mm-hmm. I said, not again. After 9 months of delay on the 8080, I said, that's it.
At the time, was there kind of a contract manufacturing ecosystem? Was there a TSMC that you could send a design to, or were you entirely responsible for also developing your manufacturing of the Z80?
Well, actually, we were able to start that way using the only company that had the process and also was providing foundry service. It was called Synaptics. There was a company that started that way with money from corporations that wanted to do integrated circuits. So mm-hmm. It was possible to use them also for, I think we were the first company ever. There was a semiconductor company to actually use foundry service.
Huh. You're the pioneer of the fabless semiconductor company.
Well, I didn't define it, but it was already. I think it was Carver Mead, the one that proposed this idea, and I think Synaptics was the first one to take on.
Okay. And
so we used them, but their yield was awful, and so so we had to quickly. Fortunately, we had an investor that had a deep pocket. So by 6 months later, we had our own fab. So
wow.
And that so we started that one too. And
that's incredible to be able to build a fab with venture funding is remarkable.
Yeah, well, in those days, the fabs were not $20 billion.
Right.
Items. So you could build a fab for with $4 or $5 million. Of course, a small fab, but still a fab properly done. And that's what we spent. Of course, in 1975, $5 million were 50 or
sure.
$70 million, today's dollars, but still, it was a relatively small amount.
That's right. Yeah, very different from what's required today.
Yeah.
Your next company was called Synaptics. Tell us what Synaptics did.
Well, Synaptics, I wanted to do computers that learn by themselves using neural networks and using analog neural networks as opposed to digital, because digital neural networks were not fast enough, and also they couldn't be done yet. So with analog, there was a way to do it. So, but they had low precision, because analog you could do about 4 bits of precision, which is good for it would have been good for inference, what people call inference these days, but not for learning. For learning, you needed a larger computer. So eventually we had to say, okay, good enough, but not, we were able to actually develop a character recognizer for Chinese, which was, used in China, and it was the first product in China where they could transform and write characters and written characters in computer form. So that actually helped China quite a bit, in about 3,000 characters. And we did that. We saw many promises. It was very clear to us by, say, 92, 93, that neural networks were the way to go. But the computers were not ready yet. Computers were too slow and too expensive to do the training. We didn't have enough data, but the technology, was clearly the way of the future. Although it took a long time, as you know, before it really took off. Partly because of the large amount of data required, and only companies like Google and so on that had large amounts of data available were able to take advantage of that. Of course, Google was using neural networks in the search engines already in the very beginning. They were not saying that, but it was very clear to me that was a part of their part of their skill was to use neural networks. What I did at that point then was, since it was clear that we were too early, I had to figure out a way, some product to make, or else close the company. Fortunately, I came up with the idea of replacing the trackball of laptops with the solid state solution, and together with 4 or 5 other engineers, we together invented the touchpad and the touch screen, which of course changed the way we do, we interface. And in '94, we had our first touchpad, and then a touch screen, of course, was already, could be available, but there was no market. And by 2000, I saw that in phones that were becoming more and more intelligent could actually take advantage of a touchscreen using gestures and so on. So we build touch screens that were able to show to customers. We were going to Nokia, Motorola, RIM, showing the touch screen and replacing the keyboards and using it, and being able to do much more with the touch screen. And they were laughing at us. And I kept insisting with my people to keep on trying, because I saw that was going to happen. Sooner or later it was going to happen. Eventually we hit Apple. Apple wanted the exclusivity, and we said no. We are not going to do that. So they made their own, and they created the market for us for second sources. So that was good. It worked out, but it took a lot of ingenuity to get there, and also insisting that was the correct vision.
So this was the birth of the capacitive touch surface. Touchscreens in the late 90s and early 2000s, listeners might remember using some of them. They were terrible experiences. They were resistive touchscreens, for the most part, right?
Those were actually, they were before they were, they required a pen and
right.
Press
a lot of pressure, only one touch.
Unusable for certainly they could be okay, not good, very good, but okay for drawing, drawing entry of drawing, because then you have a pen in your hand anyway, and then you press hard, and you can, it kind of works, not well, but it works. but not for touch, because touch is the finger. Otherwise, you would have to pick up a pen every time you want to move a cursor. Right. That would be silly, impossible, useless. Right. So they would not be useful for what we use touch screen or touch pads these days. Right. Anyway, so that made the company quite successful, as you know. Synaptics still around, and then I got interested in consciousness, and that's really what I consider my best work, even though I was part of a major change in the business.
So you've written a book called Irreducible that describes some of your thinking on this topic, and it's very relevant now, as a lot of people who use cutting edge tools from OpenAI and Anthropic and Google and others have developed a sense that there is actually a consciousness inside these tools. And you're arguing that they cannot actually achieve consciousness.
Absolutely. I mean, that is sorry to say, but it's really silly to think that a computer can be conscious. Consciousness is impossible with mechanical things, and computers are mechanical things. There is no emergent property from mechanical things. The classical bit is simply 0 or 1, and we are imposing that definition into the hardware. The hardware is analog, of course, it's not digital, but it is used as a digital structure. So if you open a computer, you don't see bit, the analog signals, but we design circuits so that they can reliably recognize a state that we call 0, which is in our mind, is not in the computer, and a state that we call 1. And so by designing properly, you can have a computer that does what we want, which is to build a machine, meaning something that responds exactly like a machine would do. And a machine cannot be conscious. Just think about it. The state of your conscious experience is actually private. You cannot, the love that you feel. Can you transfer the love that you feel, the feelings, not not the words, the feelings. Can you transfer the feelings to another person?
I think what you can communicate your feelings to another person, right?
But the communication of the feeling is not what you feel. The communication of the feeling is your interpretation. If you say "I love you," that is not what you feel. You don't feel words. You feel feelings.
It's just a signal that you're producing.
Are not classical. They are not representable with classical information. Those feelings can only be representable with quantum information. But quantum information doesn't give you, because quantum information, quantum computers are structures that do not have free will. They are deterministic structure. We are building quantum computers to perform algorithms that are realized with quantum states, but that evolve, and then eventually you make a measurement when you think they're done, and then you get the result. But the quantum computers simply are doing only the things that classical computers can do. They don't do anything different than classical computers. They can do it in certain cases. They can do it much faster than classical computers do those operations, but that's it. In fact, in the theory that I have developed, only a quantum field has the capacity to actually feel its own state. Because consciousness means that the system that is in that state actually experiences its own state consciously. So consciousness is not even in the state. The state, the way we call the state, that is a mathematical representation. The state is a mathematical thing, but the feelings is not mathematical at all, and it actually cannot occur in the classical computers, the classical system, the way we do it. That a very low temperature can behave, quantumly. So you can associate a quantum state to that, but a quantum field has much vaster properties than what we attribute now as physicists we attribute to quantum fields. And of course, they rely on entanglement. And entanglement is something that we can cause in very relatively simple systems. But, the cells of our body are actually working according to quantum and classical information in ways that we still don't understand. And those structures, which are structures in space and time, can actually communicate with the quantum fields that does not exist in space and time. It exists in a deeper reality and can communicate with the body, which is quantum and classical. That a field cannot communicate with the classical system directly. A quantum field must communicate with quantum information that interact with the classical system. But the classical system must be either designed like we design, for example, the detectors of particles. There are metastable systems that a tiny disturbance, and they can amplify that disturbance and tell you where a particle hit, for example, and things of that sort. But quantum computers are not those systems. Quantum computers are systems that are supposed to be programmed with a quantum algorithm, which of course could be also written classically because it is deterministic, but in that case could not work as fast as if you do it quantumly. So anyway, that's a big difference, and so only quantum fields have free will and can actually, and they have an identity, which is the identity characteristic of the particles, for example, of atoms that they manifest. But the atoms or particles are really the classical symbols. They are symbols in space and time. They are the excited state of the fields, which fields use to communicate with each other. So fields can actually know themselves by communicating with themselves in this new theory. Obviously not in physics. Physics considers that there's only matter and that's it. But if the theory that I have is gone beyond what quantum physics is saying, without, of course, falsifying anything that physics is saying. Physics is perfectly fine if you stop at matter, but it does not recognize that there is more to quantum fields than what they now know. And of course, entanglement is the first manifestation that quantum systems go way beyond what classical systems can do. You cannot entangle classical bits. You can only entangle quantum bits. And in other words, every classical bit is isolated from the other. There is nothing in common between a 0 or a 1 in one particular subsystem, and another 0 or 1 of another subsystem.
They're independent.
not in quantum physics. In quantum physics, you can have correlations between quantum bits that are where the real the real magic is, and those correlations are you can establish those by proper by setting them up that way. But anytime two quantum fields interact, they create correlated states among the fields, among the particles, or that we imagine are interacting. Because particles don't exist as such. Particles, quantum field theory is telling us that there is no particle, there is no object, there is an electron is not a little ball or even a wave. It is a state of the field, inseparable from the fields. Just like the wave of the sea is a characteristic of the sea. It's a property of the sea. It doesn't have its own property, and that's it. So you have to see things with a little bit more subtle ways that we have imagined. And
determinism is a characteristic of computers, and I think one of the things that often makes users of these modern AI systems suspicious is that they don't seem deterministic. Like, as a user experience, you can get different answers to the same question and have it sort of tuned, and there are these expressions of emotion that come out in the responses. But ultimately, they are deterministic. They're just deterministic at a level that no individual human can sort of fully comprehend and hold in their mind, and so it feels alive.
Well, we are attributing feelings to the computer because people that respond to us like a computer would feel. But that's only because we feeling people have taught the computer how to respond. But basically, all those parameters that contain the learning that we have taught to those computers are probabilities. So if you give a prompt to the computer, based on that particular path that the prompt sets in the sea of parameters, the computer, the algorithms, and the program will determine what is the next word that has the highest probability of following the probability of that, the structure that you have that you have already given to the computer. And so the computers will give you the next word. Now, that word is absolutely probabilistic. I mean, it is the highest probability word, which gets. Now, what happens is that often you have more than one word that could follow. So you can decide with a it's called quasi-random pattern number generator. So say you have 5 different possible numbers, possible words that can be used. You pick randomly one of those 5. So that's why if you ask the same question later, you will get a different answer, but only because in this very sophisticated structure of parameters which represent probabilities. You travel in ways in which the choice will be randomly made amongst equally probable words or equally probable states, and that's what you do. So if you do it that way, then it seems like the computer is thinking, but it's thinking nothing. I mean, it's just following whatever program we have given to it, and so it's actually it's really disingenuous to actually say that computers are actually AI is now conscious or it will be conscious in a couple of years, because it's an emergent property. No, there is nothing emergent in a computer like we're doing it. What emerges is different ways in which the computer can respond to what we taught the computer. The computer will never give you something which is completely creative, meaning something that never existed before. And I don't mean a new combination of pieces that already are known. That is, any kind of different combination, fine. There may be combinations there that have never existed before, but those combinations are not the meaning of the phrase. We are the ones that provide the meaning. We are the ones that can ask computers, for example, in different ways the same question and have different answers.
Right.
Repeat the questions, and then based on what the computer is telling us, we can see that we can have actually improve our own comprehension. And as we improve our own comprehension, we would create a phrase that would probably, it might come up randomly, but nobody would understand it.
And you don't think that we will ever arrive at a point like the Enlightenment thinkers maybe envisaged, where a computer becomes powerful enough to fully describe the human body from atoms up to neurons, and actually discover that we are deterministic systems as well?
No, because the notion of emergent property, which is emergent property, like consciousness is emergent property of the brain. No, there is no emergent properties, even in physics, are always come from quantum aspects of reality. Quantum, for example, an atom of hydrogen has properties that are much, much more than the sum of the properties of the electron and the proton that have combined. But that combination is not a classical combination. That is a quantum combination, you see? And there is a complete misunderstanding today also in physics about that. We call complexity as crazy emergent property. No. They're all related to the quantumness of reality, which is the deeper aspect where consciousness exists, where feelings, where other things exist that science is not being, hasn't recognized yet and isn't studying. But the chemical properties of different compounds, those are quantum properties. They are not classical properties. Even the for example, the properties of crystals, because the atoms are positioned in a very regularly, so that there is a huge level of coherence in that structure. Those properties are quantum properties, because if you do the same thing with the same atoms are randomly positioned, you try to make a transistor, it doesn't work. Or if it works, it has very mobilities which are hundreds of times less than what you would obtain if you have a coherent system. So we call emergent property what is not emergent from classical physics. It emerges always from quantum physics, and that's another area where there is a lot of confusion.
I'm not someone who has usually experienced emotion from AI, but occasionally I worry about what it is that separates humanity from bare computers, and so this is a reassurance to me in a way. This discussion. Do you find that it is a reassurance to a lot of people that you speak to about this, or who have read your book?
Absolutely. I mean, it's and it is dramatic what is happening today, especially in the U.S., where there is this push going on right now to believe that AI is actually conscious and it will, it will basically be better than us. And I mean, this is crazy. I mean, we are basically cutting our legs. Shooting our foot here. I mean, this is crazy what's going on. It is not possible. And it's good enough. Computers are good enough if we use them for what they're good for. But let's not go overboard and pretend that they're doing something that they cannot do.
They're just becoming better and better at making deterministic decisions.
Absolutely. And also, in imitating better and better what we do too. Because we teach them based on our own comprehension, not their comprehension, our own comprehension. We are the ones that understand and say this word instead of the other word. I mean, the trick of transformer is that we are the ones to say yes or no when the word that gets put there is better than the word before. And it's time to recognize what we're doing. Even one bit that is controlled by consciousness, by the comprehension of consciousness, can do things that cannot be done by the computer talking to another computer.
Right.
Because comprehension goes beyond the rules, beyond rules that can be explicit. So when a computer plays a game with rules to another computer, they get better and better when they play it with each other, because there are rules. And the rules are deterministic, and you cannot disobey those rules. But that is not what happens between human beings. We also violate rules, and in many cases there are no rules. We're the ones that make the rules.
I'll encourage our listeners to read your book, Irreducible, for more reflections on this. As I said a moment ago, I've found this reassuring myself. We always ask all of our guests on Go No Go to describe a go no go experience that you've had at some point in your career. Tell us about a time when you faced a go no go decision, and what did you do?
One of the early decisions of this kind was when I decided to stay in the US instead of returning to Italy. And that happened in 1968. I was supposed to stay 6 months, and I spent 57 years. So kind of an important decision. And and so what happened at that time, I was struggling a little bit, because you have to weigh pros and cons, and how do you do that? And the decision at that time, therefore, was, so I was just married, and when we came here, it was February of '68, and we were married in September the year before. So we were, for us it was almost like a second honeymoon to come here to California. Also because in Italy there was fog and so on, but we were in the north of Italy. And here, there was spring by the time we got here. So
right.
but the in talking to my wife, also it was a decision that she had to participate, of course, and so it was a struggle, But eventually I decided, no. I mean, let's decide to stay for 5 years, and then if after 5 years, we have had an experience that was, we will probably make us grow much more than if we go back. And then we decide to, and so that decision was not completely, irreversible, but, and it was interesting because very often we would say, should we buy this sofa? No, let's wait, because we don't know if we, then we have to take it back to Italy. We don't know if we're going to go back or not. So we were kind of living a little bit of, in a sort of a limbo for certain things. And then eventually, I went back to Italy after 5 years and tried to figure out if I could, if it was the right thing to do. And it wasn't. I decided then to start my first company. That was in '74. I went back and take a look, and I decided, no, that's it. We stay. And then we bought the sofa.
Wonderful. I'm very glad you did. I mean, like many of the pioneers of early computing, came from somewhere else and came to Silicon Valley and built what we have here today.
Yeah.
Thank you so much for joining us. Federico Faggin is the author of Irreducible, and his new book, Beyond Invisible, will be available in English soon. It's wonderful to speak with you today.
Thank you. Thank you.
Go No Go is brought to you by Lumafield, which was founded to upgrade manufacturing. You can learn more at lumafield.com. Go No Go is produced by Austin Carter and edited by Brian Tran, with additional assistance from Eric Petralia.